Okay, let's address now the issue about under-relaxation factors and what they are. So I mentioned this is something mainly related to steady simulations, but also you can put it in on a steady. So we're going to work in this case. It's a very small mesh. Actually, it's a 1D case. When you open Fluent, you open it as a 2D mesh and we'll get 1D. But let's, before just working in this, let's address a little bit some theory. Okay. So when we solve the Navier-Stokes, we're solving basically these equations, the general transport equation. From these equations, we can derive Navier-Stokes. So here you have how you change coefficients just to derive continuity. What the important here, remember previously I mentioned that we want the integral form in the equation. So see that this is the general transport integral form. Then you will use the Gauss divergence theorem and you convert it into a summation of fluxes. And this is the finite volume method. So we have continuity equation. Again, we go and change coefficients. You can derive momentum equations. So we are going to address some theory, how to do some discretization here. But basically we're interested in this temporal derivative. Okay, so if we keep it, it is unsteady. If we raise it, we don't use it, it is a steady simulation. So it still is a valid equation, but we are not solving for time. We don't have this change in time, that accumulation in time of this quantity that is being conserved. And again, we have it for energy and any other equation. So for instance, you can add a passive scalar or turbulence models also that are based in this equation. So you get your kx and you will see that you will exercise all this derivative in your equations. So as we have said, that as we want to solve this equation, now this is an initial value boundary problem, so we need to give boundary conditions and initial conditions. Okay, and this equation is second order accurate. Therefore, for good accuracy, we need to use a discretization method that is at least second order accurate, okay? That at least have the same order of accuracy of your equations, okay? So we're going to solve this using a method that have at least second order accuracy. So how do we run unsteady simulations using a general CFD solver? Okay, so this discussion is general, and we already did it in the previous tutorial, the cylinder. So basically, you need to select your temporal discretization scheme, set the time step, which is it's not very straightforward to do it. Okay, you need to know some frequencies in your problems, some time scales, but by monitoring the CFL numbers, you see here, you can get an idea of that. Okay, so remember that you need to choose this time step, okay, in such a way that it resolves your time dependent features, but also maintains solver stability. So the solvers that we have in Fluent and many of the commercial software, okay, are implicit. Means that they are unconditional and stable, but that doesn't mean that you can throw in any time step, because you are going to you can add numerical diffusion. We're going to see a little bit. You play with those under-relaxation factors. Then you need to set the tolerance, okay, of your linear solvers. So in Fluent, you need to set up anything. You use the default parameters, but have in mind that you can set up that, okay? You can change it. As I mentioned previously, monitor the CFL number, also monitor stability and bounding of the solution, and this you can do it by controlling some quantity of interest, okay? It's not only about colors, is also about these integral quantities. So monitor velocities in some points, mass flow conservations between inlet and outlet, minimum and maximum values of your field variables, and important also forces, okay? So lift and drag as you are doing aerodynamics. So then also, if you want to do animation and stuff by that, you need to give a saving frequency to plot your solution, so you can get that from the time step. So it's clear that you are not going to use the same frequency as the time step. Sometimes your time steps can be in the order of 10 to the minus 5. So if you save with this same frequency, you will run out of space really fast. So you will choose another frequency. Okay, so this these two scenes, time step and frequency, requires a little bit of experience, but you will get used to that. But that is the main problem in the study simulation. You need to have this information. Okay, as implied previously, no, it would save a lot of data. okay? And end of the simulation is up to you, okay? You can run 1 second, 10 seconds, 1,000 seconds, 2 days, it's up to you, okay? The point is that you need to get your data. It needs to be statistically steady, okay? It means that we saw also in the previous video, so when you average quantities, they don't oscillate too much, okay? So you need to monitor that. Okay, so when I'm talking about the time set that you need to choose it wisely, this is what we're talking about, okay? So look at here that you have, for instance, the blue line will be your actual solution, your excess solution. As you choose a large time step, see that you are missing a lot of information. So this is numerical diffusion, okay? So as you choose a time step that goes from here to here, it will be stable. It will solve the equation, but you are missing everything of your physics. So that is the importance of the time step. Here, a small time step, you resolve everything well. So you can imagine also, you can also imply here that the smaller, the better the solution, but also the more time it will take to get your solution. You need to iterate more. Also, monitor these quantities of interest. So see that you can have this behavior. So probably you are running and you are looking at this one, but you are not very critical. You will say, oh, I will stop here, because if you control also your residuals, you will see that your residuals also are going down. So it's important that be careful, just let it run, because many times you will have initial transients like this, okay? And also, if you have a solution, be also wise, where do you do your sampling, or where you are going to do, for instance, frequency analysis. So you take from the beginning up to here, we saw this, it might give you problems. So just do it when you have something that is periodic. And what will happen is you are running unsteady simulations and you actually see this behavior. So see here that we let it run 315 seconds. Here it was just after 150, you have an set. By the way, this is the same problem, the cylinder problem that we were running, okay? But lower Reynolds number, so you can try this. So what will happen is you see this. So you see this, it means that you have reached an steady simulation, okay? And steady solution. So here we're running a Reynolds number that is 20. We know that there we don't have the onset of the von Karman street, and this is the behavior. Okay, so these are typical behaviors of steady solutions when you see that your quantity of interest is not oscillating anymore. Okay, for long times, sometimes you can have them set at later times. Sometimes also what you can do is that you can force add a perturbation in the flow to see you set an instability. That instability is damped fast. You know that is steady. Okay. So what about steady simulations? We talk about unsteady. So unsteady simulations, the first thing is that it's a huge simplification of reality. And actually, I don't know many problems in reality that are steady, okay? So basically, this is a trick that we use in CFD to get fast outcome, fast solutions. We don't take into account that derivative, but somehow we need to advance the solution in time, or not in time, in an iterative way, okay? So this is where those under-relaxation factors comes into play. So in the steady simulation, so the assumption, as I mentioned, is just we ignore those in unsteady fluctuation, no more that temporal derivative, okay? And then we can perform the time or iterative averaging when dealing with this case, okay? The same way that we do with RAM, there is no problem, as we have talked before, okay? Even if we don't have this time derivative, we can do the time averaging that now we're going to call it iterative averaging. If you keep it that one, again, it's iterative averaging, but probably will be a more proper time averaging. So nothing changes, it's the same idea. The advantage of these steady simulations is that they require low computational resources, okay? Give really fast outcomes. So you see the case of the cylinder where you have the onset of the von Karman street, probably you need to run that case for a long time. Using steady simulations in a couple of iterations, probably 100 iterations, you are going to get that solution, okay? So they are really fast, but you need to know when you use it. And also they are very easy to post-process and analyze. On a steady simulation, you need to save information, monitors, you time analysis, time series, whatever. Here, just open the last file and that's all. You know that everything has been averaged. Okay, very easy to post-process. So, to run steady simulations using general CFD solver, so this discussion is general, is not only focused to Fluent. You need first to use an appropriate solver, okay? Not all solvers are made to run steady simulations. Okay, so you need to read your theory, know your theory, the user manual, whatever. Okay, and then also you need to set discretization schemes to deal with the steady simulation. So we know that we don't have that 10 time derivative, so we need to set that. Also, we don't need to set the time step. Okay, however, we need to control how the solution change from one iteration to the other, and this is done using these under-relaxation factors. Okay, so you can see that under-relaxation factor will be the equivalent to the time step, but here we don't have the time derivative, so there is some iterative method to update the solution from one iteration to the other. Okay, then as usual, residuals, controls, tolerances, you have everything. So the idea of the under-relaxation factor, as for the time state, they will be the matrix more diagonally dominant. I won't go into details about this one. This is more about CFD advanced stuff, but this is the idea about this one. So the smaller they are, the more diagonal dominant is your matrix, so your linear solver will perform better. So this is what you are doing. You have the quantity in this iteration, and you are going to control the rate of change of this quantity by using this procedure, okay, this method. So I guess you have seen this in numerical methods like over-relaxation, under-relaxation, the sort method. So you have this coefficient here, and you are going to control the rate of change. So if you put a large coefficient here, it will change very fast, will be equivalent to a very large time step. If you put it very low, it will change very slow, equivalent to very slow time step. Okay, so this is the idea of under-relaxation, and this somehow will control the diagonality of your linear system. The under-relaxation can be implicit or explicit. I won't go into details, and even into Fluent, you need to know that you will set those numbers. There is no problem, but have in mind that you have two types, so kind of explicit, implicit, and see that you can see the under-relaxation. You have this as the reciprocal of the CFL, number of kind of the reciprocal. Okay, so this is the idea of this under-relaxation. So basically, generally speaking, is you increase, usually these values are between 0 and 1. Under-relaxation can be, if you use it larger than 1, will be over-relaxation. Okay, so as you increase it and you go closer to 1, you gain speed, velocity, you will converge faster, but the fact that you are converging faster doesn't mean that you have stability. So as you increase here, you are losing stability. So see, that is a compromise. Okay, so there is no theory about this one. This is something that UNIGE is about experience and practice, or using industrial values that we are well known. Okay, so as you increase this one, probably you are losing stability. So we need to play with those values. So I mentioned, okay, it requires an experience and trial and error. Okay, but we have a standard practice. CFD has been has been around for a long time, so there are some standard values that we can use. I will give you those standard values, but generally speaking, it's not recommended to go too close to 1. It's not recommended to go below 0.1, because in one way you're losing a lot of stability, in the other way you are just gaining a lot of stability but slowing down your computations. Okay, but these values also can be changed what you are running, so you can use low values and then increase it slowly. The recommended values, okay, depending on the method that you are using. There are many methods, but here I just mentioned the simple C, simpler, PISO. Okay, these methods in their steady formulation, you can use this value. So if you are using simple for pressure, you put 0.3 and the other variable 0.7, and simple C, which is an improved version over this one, you just put pressure 1 and the other 0.1. So these are the industrial values. Okay, however, I recommend you just here stay like this, but here in the simple C put everything 0.9, or even better, put it 0.88. You gain more stability and still a good convergence rate. So what happened when I run unsteady solvers? And here let's compare to solutions. So see, the blue one is a unsteady solver. So see that you have this. You need to run for a longer time. So here I just stopping this solution at 500. So see that this one, the steady one, like in 300 iteration conversion, this one needs to iterate longer. But also you can use steady solvers on a steady flow. So here, this in case the cylinder Reynolds, I think it was 200, and see that it will give you a solution. But as you are not capturing those features, okay, you have a value. It might underpredict, overpredict, who knows? Okay, usually will underpredict, but also steady solutions will get. We can run with solutions that in fact are unsteady. So probably here you can do is run this one, stop after 1,000 iterations, okay, really fast, and then use this solution as an initial solution for this one. So you can switch for a steady to unsteady and keep iterating, okay? So this is a big advantage of steady solvers. They are really fast, but it's not guaranteed that they will capture that unsteady. So we know that for massive separation or von Karman Street, vortex shedding, stuff like that, they are not recommended. But if your flow is attached, go ahead and use steady solvers and resolve your boundary layer as well, because it's inexpensive compared to unsteady solvers. So in general, the industry standard, as I mentioned, but my recommended URF are this one, Under-relaxation. So well, I mentioned 0.8, probably you can go 0.7, and simple, this is 0.3. Okay, so, but this is up to you. You need to play with these parameters. This is what we're going to do in this tutorial. So when I was talking about the making the matrix diagonal dominant, or what these under-relaxations are doing, this is basically the criterion to have a diagonally dominant linear system. Okay, so see that your diagonal needs to be larger than the summation of the diagonal elements. So if you fulfill this, you are diagonally dominant, and these have very nice features, especially for numerical methods. Okay, it will guarantee that your linear system will converge, or at least one method will converge. Okay, so basically this is your diagonal. Okay, and what you are doing is that this value here, the summation fold of diagonal, is larger than this one, and this one will give you stability. So basically this is the idea. Okay, in under-relaxation, so now you are multiplying all these coefficients by that value. By choosing the right values, you will get your diagonal dominant. It's the same idea with time set. When you reduce the time set, also you are making your diagonal, okay, more dominant. And when you have this one, it's called the Scalar criterion, which is this one. Okay, so you are fulfilling this criterion, and this has very positive properties in linear system, iterative system. It will guarantee that it will converge. I won't go into details in that, so you can check the theory. Something about the initial conditions as well, and the iteration and those residuals. Okay, that this is important. I don't like to look at the residuals because sometimes they can be misleading a little bit, or to interpret those. Well, you need to have some experience to know what is going on, because the first time you start to do CFD, you will expect that your residuals needs to go to your tolerance 10 to the minus 3, 4, 5, whatever. But have in mind that those tolerances that you are setting there are initial residuals. Okay, and let's see how a iterative method is working. I think you have done some numerical analysis, but let's just revisit this concept. So you start to iterate, and to iterate we need an initial condition. So all variables, k, omega, epsilon, velocity, everything starts from initial conditions, and starting from that initial condition, you start to iterate. You solve a linear system up to reaching this value, which is the final tolerance. And this is important. All solvers will reach the final tolerance. This is the tolerance of your linear system. But what you see when you are plotting the residuals, looking at the residuals, are the initial residuals. In other words, the initial guess that you are using that time step on iteration. Okay, so this is why, as you understand this, it's a little bit misleading. So from this is clear that if the initial residual goes down and gets to the same values of the final residuals, that is a clear indication of a steady solution. Okay, so this is what we're doing. Okay, then you set the tolerances. This is the criteria, the linear system. So you when you give this value 10 to the minus 3, you get your matrices, your assembly. And when this is less than this one, you see you reach tolerance, and you are good to go. Okay, you pass to the next iteration or time step. Okay, so basically what we're doing, iteration phi is a better approximation of the previous one. So this is why it's a good idea to do at least also one iteration. Okay, so you are doing, especially on a steady simulation, you see that it's converging in one iteration. It's probably better to do 2 iterations, okay, because that will help in linearizing your equations. Okay, so don't it's not a good idea to go here, move here, converge, and then here you pass to the next one. Do at least 2. Okay, move here to iteration, just helping linearization. And then also it is clear that the convergence rate here depends on your initial solution. So you see that the closer that you are to your final solution here is the faster the convergence will be. So this is why at the beginning you will see that the convergence is a little bit slow, and if you give also initial values that are far from what will be the actual solution, it will be really slow. Okay, so this is what is happening there. Okay, so this is why we want to give physically realistic initial conditions and good boundary conditions just to have a fast convergence rate. So this just was this theoretical background about steady and unsteady simulation. And now let's go to this case. So this case is a particular one in the sense that we're solving is a scalar transport equation. Okay, so let's take a look at the problem that we're solving. So this is what we have. So we're solving the convection diffusion equation. So no temporal derivative. We're going to play with under-relaxation factors. No diffusion terms, so diffusion coefficient 0. So we have only convection and a source there. So see, this will be our governing equation. So integral 4 here showing just differential 4. Then you integrate and you get this solution. Easy peasy. Okay, we have an analytical solution. So we define our problem. This is our problem, 0 to 1. Okay, it will be 1D, but it's 1. You can do it 2D, and you can have triangular meshes also in 2D and see the influence of the quality of the mesh. But in this case, let's play only with URF on the relaxation factor. So the phi value at the inlet, this is the outlet boundary condition, pressure, the normal outlets, Newman condition, a velocity vector, we need to convert the solution, you need it, and then you set up your volumetric source there. So let's work in this solution. So we go into Fluent, and I have it here. And let's first, you see it's an easy one, but let me show you how to set out the source there and the transport equation. So always I like to use this vertical approach here. As you go here into parameters customization, see that you have user-defined scalars. So as you go here, right click, new, you insert a new one. So here we already have UDS one. So we're basically solving that general transport equation. So how many scalars do you want in the diffusion? You give it an index and where you want to apply it. Okay, so this is our new equation. We have the boundary condition to convert that scalar. So let's go and look at general here, steady simulations. We don't use models, no diffusion, nothing. Materials. So in materials, I change it a little bit. Okay, I put these materials. Okay, so here you have the UDS diffusion coefficient. Okay, I put it constant 0, so we don't have diffusion term in the equation. Then cell conditions. This is important. So you go here and see here that you are applying, see here that we have the source there. So if you enable source, if you don't have source there, you don't have that tab here. But as soon as you enable, click here and you set up the source there. So what kind of source there you want to add here. So here we add the user scalar, edit, and put your value, 1. We have it there. Then we go to boundary conditions. Okay, so we have the outlet, normal outlet pressure, you have the momentum here, and then the UDS, put it to 0, specify flux, which is the Newman, and then the inlet, okay, specify value is 0, okay, flux, specify flux is Newman, specify value will be the slash 0, and the momentum just give the velocity value, the one that will convert. And then the rest are wall symmetries as a standard. nothing here. The method, so let's use simple. Okay, remember that not all solvers are compatible with this steady hypothesis. Okay, so for instance, this auction that we used previously, non-iterative time advancement, is not available here. Okay, this is something to advance very fast using unsteady solvers. But we have all this family of solvers for steady solvers. We're going to play with the simple, but what we're going to do is the same for the others one. Then choose the discretization type, so see that we have everything second order accurate. Then grade solution controls, and here's where we set up the relaxation factor. So leave this one as a standard values, okay, but this is the one we are going to use, okay. This is the one that control the convection diffusion equation. So put it 0.1, nothing here. Monitors, use the default monitors, okay. Just we are going to monitor this one. This is the only question that we need to monitor. And then let's go to initialization and see what happens. So for inlet, okay, we have it. So see that we initialize with this value and we're ready to go, okay. 0 inside the domain, okay. So we didn't have anything entering inside the domain, but we have the value here defined, the initialization. And now we're ready to go. Okay, so this is a state simulation. I put here a value of 1000. So let's calculate. So see that we don't have time derivatives, and see that this is a very easy, very coarse mesh. Okay, in theory it should be very easy to solve, and see that it's taking a considerable large amount of iterations, 66 iterations, but arrive to the convergence criteria that we set in the residuals. So now we can visualize the solution. So to visualize the solution, I'm plotting that solution in a line in the middle, this line here. Okay, so we know how to do that. So we go now, XY plots, we have it here, and see our solution. So we know that it's a line from 0 to 1. See that is here is okay, but here we have a problem. So we can load also an analytical solution. You already have it there. So okay, so let me fish that solution. Okay, so I should have it here. So this is the file where I put the solution. So it will be the same format how it is output. Okay, 01. Okay. So let me fish this solution, load file. Okay, I have it here. You select, okay. You have it available. Save plot. Okay, and okay, I don't see the line. Okay, I have it here. You see you have the 2 points to add the line. That will be curve 2. Okay, and this is your analytical solution, and see that we have here some numerical error. So when we talk about diffusion, this is diffusion numerical error, okay? See that we have this problem, okay? We can get better, okay? But let me show you also the proper numerical solution. So if I go here and choose win, remember our equations of second order accurate, we are using now a method that is first order accurate. So this method will always give you a solution, but the fact that it's always giving a solution doesn't mean that it's a good solution. So we iterate again, okay, we start to iterate. So see that it's a relatively easy problem. See that we're only solving one equation here, but taking that many iteration, it's not good. And see that we load again the file. And see that now we have it shifted here. It's clearly that we start to see this is numerical diffusion. In such a simple problem, you see that we have a lot. You can imagine industrial problems. So that is why we don't use winding to get final solution. But have in mind that a wind will always give you a solution, okay? For the craziest problem, for the most complicated problem, will give you a solution, but it will add too much error to the final solution. So that's why we want second order accurate solutions. So let's go back to the second order or even higher, so you can play with the other ones, there is no problem. Okay, we know that we're having this deviation for the actual solution. So let's see how we can control that. Okay, so that we can control it here. So if I increase this one, see the increment that I will do, I will go right ahead to 1. Okay, the largest one will be super fast, but remember that you are losing stability. In this case, it's a relative easy case, so we're not losing too much. Okay, but you will see the influence here. Okay, so this is equivalent to go with an extremely large times that. So go, calculate, boom. See, 4 iterations we converge. And if we look, this is remarkably good, okay? You see that now it's much better, okay? So load your analytical solution. And this is the effect of your under-relaxation factors. Big warning, huge warning. In this case, it run, okay, with a 1. But as you go industrial cases, you put 1 here, so you go to another problem, it's steady, okay? You put 1 here, it's likely probably that it might converge or it will take longer. So see here that now I will go to a value of 0.01, much lower than 0.1. Okay, let's see what we have. So if I go here, calculate, it's clear that we know that we're going to have a much slower convergence rate. Okay, so previously it was 166, and see already now I see that it's much slower. So see that reducing this one, it will slow down the convergence. It will give you more stability. That is true, but a slower convergence rate. So it's always a good idea to have a compromise. Okay, keeps iterating and see that such a simple problem, 600, 700 iterations, too much. Okay, voila, we're here, we plot our solution again. And actually see that the fact that we arrived to our convergence here criterion, we are still not in the actual solution. So here you see that we have a problem. Iterative is a iterative convergence problem. We need to change to lower the tolerance here. So if I go to residuals here, I need to reduce this to get to a closer value. Okay, so see that we're exacerbating the problem here. So let me go back again here and let me put, so usually the pressure usually 0.3 and all the other quantities 0.7 is okay. So by default Fluent propose 1 and 1 for these two. Honestly, I don't recommend you, so go 0.07 for everything. So a standard value that you can use here is 0.7. So now we can keep iterating from this solution. Okay, then you will see that boom, in a few iterations we have that solution. We plot and it's okay. So let me show you the problem of the tolerances and having and converge solutions. So if I go here, residuals, let me reduce this one there. So this is a large tolerance, and a lot of people have seen newcomers in CFD have the tendency that you want fast solutions. So that is, everybody wants that, but you know that as you are getting fast solution, you are losing accuracy. So let's run this value, initialize. So it should converge very fast. Okay, 4 iterations. But if we look at the solution and let's see what we have, see that this is an unconverged solution. Even if you reach that tolerance that you set there, that doesn't mean that you have the right solution. And that's why I say that sometimes looking at those residuals can be misleading. You need to know very well what you are doing, especially on steady simulations. So we keep reducing the tolerance here. So I will go this one. Okay, so let's see what happens. So I don't need to restart. I keep going from there. And voila, we reach converge solution, and see that we still have a little bit diffusion there, and we know that we go to 0.01. So this is usually a steady simulation. This is a standard criterion. Okay, you can go 0.0, let's say this one. Okay, so it will take more iterations to reach that one. Okay, and we plot, and not necessarily you will have a better solution, just a different convergence criterion. So very good agreement. So now let's go back to the standard one and show you. Let me show you also the influence of initial solution. So we saw in the plot that the closer that you are to your initial final solution, the faster the convergence will be. So let's put here a crazy value. Boom, boom, boom. For this one, and let's see what happens. So if I start to iterate, see that It's going up and then going out. So it is converged, but see that at the beginning it's going on. And it might happen in some cases that if you are very far, it will keep going on, it won't stabilize, and then it will diverge. So this is why it's very important to give good initial conditions, especially with those turbulence variables that we compute. Okay, remember that those k, omega, epsilon. Okay, the turbulence models can be very sensitive to these quantities. So usually Fluent does a good work estimating those initial quantities, but also you can do it manually if you want something better or you feel that what you can compute is better. So see that good agreement. So the other experiments that I want to do, so we go back to one. Okay, so let's make it diverge. Okay, so remember that I talked about over-relaxation. So in theory, over-relaxation should be super fast. So over-relaxation here, you should put a larger than 1. But you see that you cannot put it because Fluent is also telling the values are limited between 0 and 1. So this is kind of a safety measure, okay? So to put something larger than 1 there, you need to go to here to your text user interface. So you go to solve, okay, you enter, you have the option set. Then I want to play around with under-relaxation. So you need to write the whole number, just the first letters, okay, boom, under, and then you can set under-relaxation factors here. So see, I would set UDS and I will put 1.4. Okay, you see you have it there. And now as you run, calculate, bam, 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 and see that it's not converging. Okay, so it'll remain here stalled. So you can let it there up to 10,000 and won't do anything. So in theory, you may imagine that it will go faster, but no, it's not going faster. Okay, so be careful. Do not under-relax. And actually, it's diverging. You don't have any value there. So if you can plot also. We haven't plot solutions here. See that infinite actually diverge. Okay, and see that. This is another problem. You are looking monitors here, and it's telling you that, okay, it is stalled, but it's not going larger than 1. But actually it's diverging. Your values are infinite, okay? So these are things that you don't see in this one. Again, another reason not to fully look at these monitors. So let me go back just to show you to be sure, okay? Here, go back half, 0.7. And if I try to run from this solution, let's see what happened. Okay, adjourn. It will see that it's taking longer time to iterate. Maybe it will converge. Let's see what happened. Okay, boom. Okay, since that it converges, it visualized here, and see that this is the solution. Okay, linearly varying from 0 to 1. And this was quite cool. Okay, you saw here the effect of a bad initial condition. Okay. See that all these oscillations, and you can see that everything can be controlled. So if you choose here a lower under-relaxation, you will smooth this oscillation, but it will take much longer to converge. And you have your solution. So the last experiment. So feel free to play with this case. You play with this under-relaxation. Also feel free to do another measure. So your domain from 0 to 1. Okay, you can do 2D. Also or 3D, but let's move to transient. Okay, so transient, exactly the same, nothing changed. Here you choose your discretization. See that now your access time derivative, go second order here. You can also set under-relaxation. So here, remember that the time step is the one that it will go into your matrix and it will make it a diagonal. So there is no need to play with this under-relaxation, but you can add more stabilization. Okay, so there is no need to use the industrial value. So it's better if you go Unsteady, put this one all to 0.7. Okay, so this one will give you more stability. Okay. And then we initialize. You go here, run calculation, and just put your timestamp. And this is up to you. So we know, okay, probably it's too large. Let me put this one, 20 iteration maximum, okay. And it goes, and see that is going from initial solution. Okay, let's finish. Okay, so see, initial solution until reaching your tolerance. Okay, the tolerance, where do you set that tolerance? In the case for this solver here. And when you reach this one, go again, initial residuals, final residuals, initial, finals, okay? And as you see this behavior that your initial residuals goes to your final residual, means that you are reaching a steady solution. And let's visualize what we have. Okay, since that is okay, if I plot again here, the solution. So you see that this one, it is iterating more than the steady, okay? It's doing, besides outer iterations, inner iterations, so they are more time consuming, these solvers. For instance, let me go again, let me initialize, and let me go here, controls, and let me put here a very small value, 0.01, and you will see that also it has an influence in your convergence rate, okay? Immediately you see, okay, the influence. So it says calculation complete. Maybe it is, maybe you will have the impression that it's converged, but look at that, is just propagating the solution very slowly. Okay, so it will take much larger time. So even, let me go here and put a time instead of 5. Have this jump. Let's see what happened with the solution. Okay, still it's very slow, the propagation. So as you go here, and let's put it 0.1, it should be okay, this value should go fast. Okay, so see that now it's converging slowly. But here, you have the influence also the time step that is very large, and now it's going down, okay? And again, as this is steady, you can save all time step and you will see the animation how this is propagating. Also, you can, on steady, that was also for a steady, you can do it. You can save all your iterations and see the propagation, but you have the time variable will be iterative propagation. Do you know if iteration 10 correspond to a second 0.1 and so on? Instead here, you know that each iteration corresponds to this time as it is conserved. So nice case that you can play with all these solvers and get a feeling of the under-relaxation factors. I recommend you, okay, that sometimes the default values, they are not ideal. So you go here, default, get this one. So if you are using simple and steady, these are your ideas one. Remember 0.3 pressure, and the rest put it to 0.7. If you are doing you are using simple C. Simple C is an improvement of the simple that it use different under relaxation. So, but see that Fluent is not giving the right value. So remember, simple C will be everything 0.7. This is critical because if you use too low pressure here for simple C, it might converge very slow and sometimes it will diverge. You have piezo. Piezo have also some under relaxation factors requirements similar to simple C, 0.7. And then we go to the couple, okay? This is another problem. This is the most robust one for a steady simulation. So remember, the couple for a steady is really good, but going on a steady using the couple doesn't make sense because it used too many computational resources, okay? So you see that you set up these explicit relaxation factors, okay? So have these default values that probably these are okay. Sometimes you might need to increase. So let's go here with this one and let's initialize, and you will see that a huge improvement in this one. So calculate, boom, in 4 iterations we have a solution. So let me go here, it's okay. And let's go back to the simple. Okay, so we're using here default values, initialize, calculate. Okay, same number of iterations. Let's go with the piezo. Okay, default values, initialize. That are not the ideal one. Initialize. Okay, and run. Oops, no, now I can run. Okay, in 4. So probably it's better to reduce this one to 0.7 just to get an idea. Okay, let me go here, piezo, in 18 iterations. So as you will realize also that all methods will have different convergence rate. This is okay. So usually the piezo is something that you would use for unsteady. So you go steady state for simple C, or coupled. Piezo is formulated for steady, for unsteady. Sorry, and let me now initialize here 0.7. So this one was 18 iterations. Okay, don't forget that number. And we go here, calculate again. Okay, 18, same value, about the same. So okay, this is all. This is the how to play around with our under-relaxation. So in the next tutorial, we'll prepare another pipe, a little bit different for what we have done so far, but we're going to play with steady and unsteady, and you will see better the influence of the relaxation. For here, I hope you get a good idea where are those numbers. Bye.